Hey there, Algebra. We are in Unit 2, Lesson 2. Doing great. So, last lesson we talked about modeling some situations. Today we're going to keep on going with that and talk about writing equations to model these situations or relationships. Okay? So, let's look how equations can help us describe relationships and constraints. I'm going to go to the end of the slide and show you what that constraint word means. Wait for it. There it is. A limitation on the possible values of variables in a model, often expressed by an equation or an inequality, or by specifying that the value must be an integer. That's important. Integers, they're whole numbers, okay? 1, 2, 3, 4 integers. For example, distance above ground, d in meters, might be constrained to be non-negative, expressed by d is greater than or equal to 0. That's a constraint. Distance has to be a positive number. The amount of pizzas you purchase has to be a whole number. Things like that. Back to the beginning. We did this page. All right, so let's warm up a little bit. Evaluate mentally. 25% of 200. I think about 25%. I think about quarters. There's 4 25-cent pieces in a quarter in a dollar. So 25% of 200 is a quarter of 200. My tablet's not on. Let's go back to, oh gosh, there we go. Sorry, my tablet wasn't on. So 25% of 200 would be a fourth of 200, or just plain old 50. Okay? 12% of 200 to me is not quite as easy. I can do 10% of 200, which is just moving the decimal place over 1, and that's 20. And then that's 10%, and then 2% is like 4. So 1% would be 2. Do that twice, it's 4. So 24. 8% of 200, I know that 1% is 2, and if I do that 8 times, that's 16. And then p% of 200. P% of 200 is, I could say either, let's see, how did I do this one? I did 1% of 200 times 8. So if we change this, I can say 2 times p%, just like here. This is really 2 times p%. Okay, here it's 2 times p%. All right, 2 times p%. So here it's 2 times p%, which works. Or I could do p over 100 times 200. That one's not as intuitive to me. 2 times p% makes sense though. Do you see how we just took something that we were evaluating mentally and we put an equation to it? Okay, we put that equation to it to try to make an equation that will work with anything. All right. These three figures are called Platonic solids. In what ways are the three figures alike? In what ways are they different? All right, start dreaming about it. What ways are they alike? What ways are they different? Let's do alike here. I'd say they're all 3D, three-dimensional figures. Okay, they're all 3D. Let's see. They all have sharp edges. They all have vertices. Like this is called a vertex. That's called a vertex. It's where the faces meet. These would be the edges. Okay, edges, vertices. They all have faces. That's what those are called. Let's say that. Like this right here is called a face. And then I have an edge and a vertex. Okay, let's try how they're different. They all have different number. I don't know who that was. Different number of faces. Different number of vertices. And different number of edges. Okay, so that is how they are all different. What other ways can they be different? I like this one. I just looked at my notes. They're made with different polygons. Different polygons, like the tetrahedron, The tetrahedron, oh goodness, is made of triangles. The cube is made of squares, and the dodecahedron is made of pentagons. Yep, all pentagons. So they're made of different polygons. All right, that all works. Let's take it a step further. I don't know why we have this one again. All right, the table shows the number of vertices, edges, and faces for the tetrahedron and dodecahedron. Okay, complete the missing values for the cube. This is actually not filled in. So let's do that really quick. Tetrahedron has 4 faces, okay, 4 vertices, and 6 edges. Let's check that. Tetrahedron, 4 faces, so 1, 2, 3, 4. So you've got the 3 on the top and then the 1 on the bottom. 1, 2, 3, 4 vertices, and then 1, 2, 3, 4, 5, 6 edges. Yep, that's true. Dodecahedron. Okay, I've got 12 faces, 12 pentagons, 20 vertices, and 30 edges. All right, let's complete the missing values for the cube. I'm looking at my paper. I bet you can look at yours too. I've got 1, 2, 3, 4, 5, 6 faces. Vertices, 1, 2, 3, 4, 5, 6, 7, 8 vertices. And edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. Okay? Then make at least 2 observations about the number of faces, edges, and vertices in a Platonic solid. Well, the number of edges is always biggest. Okay, the number of edges is always greater than either the faces or the vertices. What else? I love numbers, so I see that they're all even. All the numbers are even. That's pretty cool. The number of faces, I guess we can say the number of faces is less than or equal to the number of vertices. Because here it's equal to, here it's less than, here it's less than. So the number of faces is always less than or equal to the number of vertices. That's something. Let's erase that. I don't want to confuse it. If we look at the number of edges, let's see. If I do this, 4 plus 4 is 8, minus 2 is 6. See if we can do that again. 16 plus 8 is 14, minus 2. Cool. Cool. There's a pattern. 12 plus 20 is 32, minus 2. Cool. The faces plus vertices minus 2 is edges. There are some interesting relationships between the number of faces, edges, and vertices in all Platonic solids. For example, the number of edges is always greater than the number of faces. Another example, the number of edges is always less than the sum of the number of faces and the number of vertices. There is a relationship that can be expressed with an equation. Can you find it? If so, write an equation to express it. We found one. We did it in numbers up here. Okay, let's do it with letters. So I can say faces plus vertices minus 2 equals edges every time. Okay, faces plus vertices minus 2 is the number of edges. I could put those in any order. I could say vertices plus faces minus 2 equals edges. Okay, I could also say faces plus vertices equals edges plus 2. Crazy one, isn't it? I could say that too. All right, cool. Let's move on. Blueberries and earnings. I love blueberries. I actually talked the family into going blueberry picking this summer, and I was the only one that enjoyed it, and everyone ate them. But I love blueberries. They're delicious. So let's write an equation to represent each situation. All right? Blueberries are $4.99 a pound. Diego buys B pounds of blueberries and pays $14.95. So I can do $4.99 a pound times B, however many pounds Diego buys, and that's going to be $14.95. Okay, so there is an equation that represents this situation. Now, blueberries are $4.99 a pound. Jada buys P pounds of blueberries and pays C dollars. So I'm still at $4.99 times P pounds, and she spends C dollars. We don't know, so we have to put a letter there to hold the place. All right. Blueberries are D dollars a pound. Lynn buys Q pounds of blueberries and pays T dollars. Do you see what we're doing there? Slowly, I'm taking away the numbers and just putting in the letters. So we have D dollars a pound, Q pounds, T dollars, total dollars. Let's see what else I can do. Noah earned N dollars over the summer. Mai earned $275, which is 45 more than Noah did. Okay, so Noah earned N dollars over the summer, and Mai earned $275, which is 45 more than Noah did. So Noah plus 45 equals 275. Or I could say Noah earned 275 minus 45. Those are equivalent. They mean the same thing. Sorry, we're going to try to fix that. Okay, those are equivalent. Noah earned $45 less than Mai, and we know how much Mai made. Or Noah earned $45 more than Mai, and Mai made... Oh no, the amount Mai made is 45 more than Noah made. Sorry, I got it all confused. All right, let's see if we can take it further. Noah earned V dollars over the summer. Mai earned M dollars, which is 45 more than Noah did. So Noah's plus 45 equals Mai. Or I could say Noah equals Mai minus 45. Either one works. All right, Noah earned W dollars over the summer. Mai earned X dollars, which is Y more than Noah did. So Y more than Noah is Mai. or Noah is my minus the more. All right, how are the equations we wrote for blueberry purchases like the equations we wrote for my and Noah's summer earnings? So I'd say they're the same because for the blueberries, each equation represented the same information, okay? Each equation did a great job of representing, let's say, the three quantities. Okay, we can do that for the blueberry and the summer earnings. Each equation represented three different quantities that we messed with. The first equation, it had two known quantities for the blueberries and the summer earnings. The first equation had two known quantities. The second equation had one known quantity, and then the third equation had zero known quantities. So that's another way that they're equal. All right, I'm actually going to stop this lesson now and continue it in a little bit, okay? It is lunchtime.